Hello again, students. So again, on Monday, February 11th, we ran out of time before we could look at a solution for number 73 from chapter 7. So I'm going to discuss it here in the video. And if you have additional questions, you're going to ask them either by email or before or after school on Tuesday, or even in class on Wednesday before the test. So 73 is some skidding, cars, and collisions. You've been hired as an expert witness in a court case involving an automobile accident. The accident involved car A of mass 1,500 kilograms, which crashed into stationary car B of mass 1,100 kilograms. The driver of car A applied his brakes 15 meters before he skidded and crashed into car B. After the collision, car A skid 18 meters while car B skid 30 meters. The after picture, I've sort of drawn them side by side because I couldn't figure out how to draw them in front of each other, but presumably A crashed into B, B moved at a faster speed than rest to the left of B, and both came to a stop. The coefficient of kinetic friction between the locked wheels and the road was measured to be 0.6, showed that the driver of car A was exceeding the 55 mile per hour or 90 kilometer per hour speed limit before applying the brakes. So we want to know, how fast was car A driving before the collision? We have 15 meters of skid marks before colliding into car B, but I think we can kind of put that off to the side. That's going to come later. What we want to know is what happened just before the collision and after the collision. So we have car A encountering car B, so this would be like the collision speed. We can then work backwards from the skid marks and figure out how fast car A was going before beginning the skid, and answer the question. So we now need to look at the skid mark information of car B and car A to figure out how fast car B and car A were going just after the collision. So we have a not perfectly inelastic collision. However, we have enough information to know the ending velocity of car B and car A separately, and then we can work backwards to find the beginning velocity of car A before the collision. So we need to figure out what was the ending velocity of car B and the ending velocity of car A given their skid mark info, and then we'll consider the collision. So we're thinking about, we can either think work done by friction and change in kinetic energy, or we can think about force of friction, acceleration, and kinematics. And maybe I'll show you one each. So for B, I'm going to say that the force causing B to stop was the force of friction between the tires and car B. And for that 30 meters, car B skid, car B came to a rest, losing all of its kinetic energy. So 0 kinetic energy at the stop end minus half times the mass of B times that velocity just after squared. So I'm saying work done by friction is equal to loss of kinetic energy, and the work done by friction is negative because friction points in a direction opposite to the motion. Then we know that friction is mu sub k, because it's a slide, times weight times distance, right? So mu sub k times weight, that's the mass of B, equals half mass of B times ending speed squared. Ending speed, I mean speed after the collision squared. I can factor mass out, and I can actually solve now for the velocity of B, which is equal to the square root of 2gd. Oh, mu sub k gd. And so mu sub k is given to be 0.6, and g is 9.8 meters per second squared on Earth, and car B slid 30 meters, and we're taking the square root of that mess. So 2 times 0.6 times 9.8 times 30, and I'm taking the square root to find a speed of 18.8 meters per second for car B just after the collision. So I said I would show you the Newton's second law kinematics version for car A. Again, we need to find the force of friction. I'll try to use similar notation. So the force of friction on car A. So car A experiences a force of friction equal to mu sub k times normal force. That is mu sub k times mg, where that's the mass of A. So again, it's 0.6 times the mass of A times g, 9.8. So we get a force of friction of 8,820 newtons. And then we know that A must have a deceleration equal to the force of friction divided by its mass, which again means we never really needed to know the mass of the car, just as over here mass factored out. So I have the deceleration of A of 5.88 meters per second squared, and then I'm going to choose the v squared kinematics equation, and I have a negative sign here because I know it's its slowdown. So the ending speed, the starting speed, this would be 0 because it comes to rest. This would be the starting speed, which is the speed of A just after the collision, so I'm calling it VA final, referring to after the collision, squared minus 2A delta x. So VA is equal to the square root of 2A delta x, or the square root of, I'm not going to be able to fit it all on here, but 2 times 5.88 times 18 meters of sliding. .5 meters per second. Okay, so now I know the green velocity of car A just after the collision is 14.5, and I know the orange velocity of car B just after the collision is 18.8 meters per second. So I know the velocities of the two cars just after the collision, and I'm going to use conservation of momentum to work backwards to find the velocity of car A just before the collision between the two cars. So I need a little more paper and a little more room here. I want to keep my diagram, however, because I want to highlight the fact that this is an inelastic collision. I'm going to model it as an inelastic collision where I have momentum before, actually I'll just use subscript, right? Before equals momentum after of the system, where I have two cars. So I'm looking at car A's mass times its velocity before the collision, car B's mass times its velocity before the collision, car A's mass and its velocity after the collision, which I just found, and car B's mass and its velocity after the collision, which I just found. So I know that car B is stationary before the collision. I know car A's mass, 1,500 kilograms. I'm going to drop units because I probably won't be able to fit this all on the page. Car A's mass is 1,500 kilograms. Car A's velocity just before the collision is what I'm looking for here. Car A's mass, again, is 1,500 kilograms, and its velocity just after the collision, based on its skidding, is 14.5 meters per second. Car B's mass is 1,500 kilograms. Car B's velocity just after the collision, according to its skid marks, is 18.8 meters per second. So now I'm just doing a bit of basic math, right? 1,500 times 14.5. And I'm going to have some rounding errors here. If I had saved more digits for my velocity, I would have a more accurate calculation, but I don't really care. I just want you to see the concept here. All right, so for car A, after the collision, I have 21,750 kilogram meter per second momentum. For car B, after the collision, I have 28,200 kilogram meter per second momentum. They're both sliding to the right, so these are both positive. And all of that momentum came from the fact that car A came into this collision at some starting speed, and that's again what I'm looking for. So total system momentum is 49,950. The velocity of car A before the collision, according to this, then, is 33.3 meters per second. So car A slides into this collision, right? So it had been skidding for 15 meters. As it enters the collision after that skid, it's going 33.3 meters per second. And now we want to know, car A, sliding into this collision, had been decelerating already. It skidded, right, there's the skid marks, for 15 meters before the collision. And we're like, well, okay, how fast was that car going then coming into the skid? How fast was car A going right before it put on the brakes, slowing itself for 15 meters to 33.3 meters per second? And so we're back again to the same idea as before, that the force of friction caused a loss in kinetic energy, or the force of friction caused a deceleration, using kinematics to figure out what happened. So I can say that the force of friction on A, we actually happen to do that for A, is 8,820 newtons, causing a deceleration of 5.88 meters per second squared. The sort of details for A are the same, whether A is skidding over here or skidding over here, because it's the same car doing the same deceleration for the same friction force reason. So I don't even have to do that again. I can just say acceleration is 5.88 meters per second squared, or rather deceleration, right? And then I can say, well, the final velocity squared equals initial velocity squared minus 2a delta x. The final velocity is 33.3 meters per second. The starting velocity is what we are trying to find, and it decelerated at 5.88 meters per second squared due to the friction between the tires and the road, and it did so for 15 meters. So VI squared is equal to 33.3 squared, so 1108.89, plus 2 times 5 plus how much further it went because it was slowing as it skidded, 5.8, or how much faster it was going because it skidded and slowed. So that's 176.4. And then I need to take the square root to find the starting velocity. So I have a starting velocity of 35.9 meters per second. And then we need to compare that to miles per hour. I'm actually just going to find my phone if I can. It's actually somewhere in a pile on my desk. But let's find what 35.9 meters per second is in miles per hour to answer the question. And I may not, so it's 80.306 miles per hour. And I forgot what the speed limit was, but this person was clearly exceeding the speed limit. 55 miles per hour for the speed limit before applying the brakes. Unless I've made an error in calculation, this person was speeding a whole lot. Let's check out the solution. Interesting. The pre-collision speed here is not as fast. I wonder what error I've made. I think I mixed up my distances somewhere. Nope, that's 30 meters and 18 meters, 14.5 and 18.8. No, those are correct. So 28.32. Interesting. Okay, the solution has a speed here of 28.32 to my 33.3. So I must have made an error in calculation, but I can't find it. And then they have a right before collision speed of 31.28, which translates into 70 miles per hour. In both cases, we find that the car was speeding, but I must have made an error here in my momentum calculation. I've been recording for 15 minutes and you're tired of hearing me, but I don't know how to pause and edit this video. Let me see if I see the error. I see the error. The second car's mass is not 1,500, it's 1,100 kilograms. So I've overestimated the system momentum because I've given the second lighter car a much larger mass. So in any case, the solution says this is 28.3 meters per second, and this then is 31.2 meters per second. I may re-record this video and repost it tomorrow, but I wanted to get it out to you as quickly as possible. So please, again, email me questions if you have any, or be ready to ask right before the test on Wednesday afternoon.